Penguin Random House Audio presents The Matter of Everything: How Curiosity, Physics, and Improbable Experiments Changed the World. Written and read by Suzie Sheehy.
Introduction. Some years ago, I was sitting at a laptop frowning at the seemingly easy question I'd just been asked by 4 particle physics professors from the University of Oxford. I'd missed their names, not just from nerves, but because my PhD interview was conducted over an unstable internet connection from a motel room in outback Australia. They'd asked me, "What do you find fascinating about particle physics?" This was a trick, surely. Oxford admissions interviews are notoriously tough. In that moment, I decided it was best to be honest. I told them of my wonder at the way physics seemed to be able to describe everything, from the smallest subatomic particles to the atoms that make up our bodies, up to the largest scales of the universe, and how all of this was connected. Particle physics, I said, was the foundation of it all. 5 years earlier, I'd been studying civil engineering at Melbourne University. I'd never known that being a physicist was an option. While I'd enjoyed physics in school, I'd only ever known of it leading to a career in engineering. That all changed a year into my university degree, when I was invited along by my classmates to the annual highlight of the Physics Student Society calendar, Astro Camp. One Friday afternoon, we left Melbourne and arrived 2 hours later at the Leon Mao Dark Sky site. The bumpy dirt road led us to a tin-roofed building where we unpacked beer and telescopes, then set up our tents near a large clearing. As the light faded, the temperature dropped and the sound of cicadas began to pierce the air. And to preserve my night vision, I used a hair tie to hold a piece of red cellophane over my torchlight. I clambered into my sleeping bag, grateful for its dual function as a source of warmth and an insect barrier. I breathed in the familiar scent of gum trees. Then I looked up. "There's one," the man next to me shouted, as a meteor blazed across the sky. As my eyes adjusted to the darkness, the true wonder of this designated dark sky site revealed itself. The chatter fell to whispers, which in turn fell to a hush. Venus slowly set below the horizon, and other planets came into view. Over the course of that night, I got a sense of the slow but constantly changing nature of the night sky. Through my friends' telescopes, I saw the magnificent rings around Saturn, familiar from pictures but strangely new through a lens. Stars forming in nebulae full of glowing dust, and globular clusters sparkling with millions of stars orbiting our galaxy 100,000 light-years away. The most spectacular view was the bright band of stars and dust, the glowing arc of our own galaxy, the Milky Way. From the southern hemisphere, we look towards the middle of our disc-shaped galaxy. We're about 2/3 of the way out from the middle, orbiting our star, which itself is moving within the Milky Way. The galaxy is cruising through space along with its local group of galaxies at about 600 kilometers per second. Beyond it are billions more like it: stars and nebulae, black holes and quasars, matter formed from energy, transformed through immense tracts of space and time. That moment was when I truly grasped how small I was, how short-lived, and how I struggled to put words to the magnitude of what I was seeing. The stars and planets weren't up there, and I wasn't down here. It was all part of one enormous physical system called the universe. I was a part of it too. Of course, I knew that already, but I'd never really felt my place in it until that moment. Suddenly, nothing else mattered. I wanted to know more about gravity and particles and dark matter and relativity, about stars and atoms and light and energy. Above all, I wanted to know how it was all connected and how I was connected with it. I wanted to know if there really was a theory of everything. I felt deeply that this all mattered, that it mattered to me as a human, that understanding this was a goal big enough that if I managed it even a little bit, I'd not have wasted my blip of time as a conscious being. I decided to become a physicist. The aim of physics is to understand how the universe and everything in it behaves. One of the ways we try to do this is to ask questions, and As I studied more physics, the question that seemed to lie at the core of it all was, what is matter and how does it interact to create everything around us, including ourselves? I suppose I was trying to figure out the meaning of my own existence. Rather than study philosophy, I went about it in a more indirect way. I set about trying to understand the entire universe. People have asked questions about the nature of matter for millennia, but only in the last 120 years has this curiosity finally led us to some answers. Today, our understanding of the tiniest constituents in nature and the forces that govern them is described by the field of particle physics, one of the most awe-inspiring, intricate, and creative adventures that humans have ever embarked on. Today, we have intimate knowledge of the physical matter of the universe and how it all fits together. We've found that reality has a richness and complexity that humans just a few generations ago could never have imagined. We've overthrown the idea of atoms as the smallest bits of our world and discovered fundamental particles that play no role in ordinary matter, but appear necessary based on the mathematics that, somewhat miraculously, describes our reality. In just a few decades, we have learned how to fit all of those pieces together, from the blast of energy at the start of the universe to the most precise measurements in nature. Our view of the smallest constituents in nature has changed rapidly throughout the last 120 years, from radioactivity and the electron to the atomic nucleus and the field of nuclear physics, together with the development of quantum mechanics, which describes nature on the smallest scales. Some way into the 20th century, this work became known as high-energy physics, as new particles were found and the focus shifted away from the atomic nucleus. Today, the study of all the many particles and how they are formed, behave, and transform is simply called particle physics. The standard model of particle physics classifies all the known particles in nature and the forces through which they interact. It was developed by many different physicists over decades, and our current version came about in the 1970s. This theory is an absolute triumph. It is mathematically elegant and unbelievably precise, yet fits on the side of a mug. As a student, I was drawn in by how completely the standard model seemed to describe how nature works at a fundamental level. The standard model tells us that all the matter that makes up our everyday existence is composed of just 3 particles. We consist of 2 types of quark called up and down, which form our protons and neutrons. These 2 quark types, together with electrons, make up atoms, held together by forces, electromagnetism, and the strong and weak nuclear forces. That's it. That's us and everything around us. Yet, despite being composed of nothing more than quarks and electrons, we humans have somehow figured out that there is much more to nature than this. Our triumph of knowledge has not come about purely through conceptual and theoretical leaps. The stereotype of a lone genius theorizing at a desk is largely incorrect. For over a century, questions like what is inside the atom, what is the nature of light, and how did our universe evolve, have been addressed by physicists in an entirely practical way. The reason we can say today that we know all this stuff, that we think our theoretical models represent reality, is not because we have pretty mathematics, but because we have done experiments. While many of us come across the idea that protons, neutrons, and electrons make up the world around us as children, very little is said about how it is that we learned about matter and forces and, well, everything. A proton is a million times smaller than a grain of sand, and it is far from obvious how we actually go about working with matter on so small a scale. This is the art of experimental physics, to follow our curiosity from a seed of an idea to a real physical piece of equipment to the accumulation of new knowledge. That evening at the dark sky site, that understanding that I enjoyed physics more when I got to experience it firsthand, led me towards the idea of being an experimental physicist. While theoretical physicists can revel in mathematical possibility, experiments take us to that frightening frontier of vulnerability, the real world. This is the difference between theory and experiment. while a theoretical physicist.
Sample complete. Ready to continue?